Okay. Thank you very much, Fatih, for the introduction. Do you hear me all right?
Yes.
Okay, great. So indeed, I'm going to talk about the Burer-Montero factorization. It's a joint work with Irène Waldspurger from the University, from the Bern Institute in Groningen. The Burer-Montero factorization is a heuristic for solving semi-definite programs. So in all the talk, we'll consider semi-definite programs with generic semi-definite programs. So of the form, minimize the trace of Cx under the constraint that A of x is equal to B and x is a semi-definite positive. So here x is the unknown, it's a square matrix with size n. C is also a square matrix with size n, it's called the cost matrix. A is a linear map with image in Rm. So it captures m linear constraints, and B is fixed and known, it's a vector with m coordinates. More precisely, we're going to be interested in semi-definite programs where we know that there is an optimal solution with low rank. So we are interested in low rank semi-definite programs. The motivations for this are diverse. It's been known for quite a while that there are many inverse problems actually, which have a low rank structure. So maybe the most well-known of them is matrix completion, but there are many others. It's in particular a structure which appears when you want to solve an inverse problem where you must reconstruct some signal from quadratic measurements. So phase retrieval, for those who know phase retrieval, is a typical example. So when you want to solve such problems, a way you can do it is to lift the problems to a matrix space. So you do a suitable change of variable, and then you get a semi-definite program which can be shown to have in some cases a low rank solution. And if you are able to find the low rank solution, then you exactly solve your initial inverse problem. So this is to say that it's a structure which appears in many inverse problems. You have to stress the fact that I have a link with the topic of the workshop. And if you want to solve a low-rank semi-definite program, you can. So the first idea is to try to apply a generic semi-definite program solver to your problem. So this is doable. There are many numerical solvers which apply to generic semi-definite programs. For a fixed precision, they work in polynomial time. So at first sight is fine, but the order of the polynomial is typically large. So for instance, the most well-known family of semi-definite program solvers is interior point methods. And when m, the number of constraints, and n, the dimension, are of the same order, interior point solvers typically have a complexity of the order of n power 4 at each iteration. Meaning that when you want to consider relatively high dimensional semi-definite programs, it's essentially out of question to use a standard numerical solver. The complexity is just prohibitive. So since we know that we're interested in semi-definite programs with a low-rank solution, a natural idea is to exploit the fact that there is a low-rank solution. So as I said, there are many situations where semi-definite programs have a low-rank solution. It's the situation that we're interested in this talk. actually, it's known that for geometric reasons that any semi-definite program has at least one solution with rank of the order of square root of 2m. So I recall that m is the number of linear constraints, but for the problems that we are interested in this talk, the rank will rather be of the order of 1, so typically between 1 and 3. And there are two main strategies to exploit the fact that there is a solution with low rank. The first family of strategies is Frankfurt methods, and the other family is the Burer-Montero factorization. So both strategies are interesting and valuable, but in this talk I will focus only on the Burer-Montero factorization. So before explaining what my talk exactly is about, let me describe the Burer-Montero factorization. So I call R optimal, R opt, the rank of the optimal solution. So it's a small quantity. And let's imagine that I choose some integer p, which is larger than R opt. Then, since I know that there is a solution with rank R opt, I can write the unknown x as under the form VV transpose, where V is a matrix with n rows and p columns. The solution, since it's semi-definite positive and it has rank at most p, it can be written under this form. So I can write my unknown like this, and instead of directly optimizing over x, I can optimize over b. So the factor with n rows but p columns. So if I do this, so I replace x by VV transpose, I get an equivalent problem which has the form minimize the trace of C VV transpose over all matrices V, which satisfy the constraint that A of VV transpose must be equal to B. Note that I dropped the semi-definite positiveness constraint because a matrix of the form VV transpose is always semi-definite positive. So these two problems, the one at the top and the one at the bottom, they are exactly equivalent, provided that P is larger than R opt. And let me stress out the fact that P, it's an integer, which is called the factorization rank. It's a parameter of the factorization. It's something that you must choose. The only constraint is that it must be at least equal to R opt, possibly larger. And the choice of this parameter will have an important influence on whether the equivalent factorized problem will be easy, cheap, difficult, expensive to solve. So it's an important parameter. So the factorized problem, how can we solve this? So let's assume that the set of all matrices V which satisfies the constraint A of VV transpose equals B is a manifold, and moreover that it's a nice manifold, in the sense that we know this manifold sufficiently well so that we can run Riemannian optimization algorithms on this manifold. So then we can precisely consider applying Riemannian optimization algorithms to solve the factorized problem that we have. And if we do this, we can hope to have numerical methods which solve the problem in a significantly smaller amount of time than generic semi-definite program solvers. Indeed, in the factorized formulation, the unknown V, it has n times p coordinates, and p is typically much smaller than n, which means that the number of unknown coefficients which we must reconstruct is much smaller than n squared, which is the number of coefficients in the original unknown x. So when we've factorized, we've reduced the number of unknown coefficients. And so we have hope, we can hope that one iteration of a Riemannian optimization algorithm will be much cheaper than one iteration of a semi-definite program solver. So we can expect a high computational gain. However, the factorized problem is not convex. The original problem was convex, but the factorized version is not. And as a consequence, it's in theory possible that Riemannian optimization algorithms get stuck at some critical point of the problem instead of finding a global minimizer. So this issue is real, it can arise, but it's also possible that it does not rise. And this depends on, in particular, on the choice of the factorization rank. Hence, the following question: how must we choose P? Ideally, we want P to be as small as possible, because the smaller P is, the smaller the number of coefficients we have to reconstruct is. So if P is smaller, numerical solvers will run faster, but we still want to choose P sufficiently large so that our algorithms do not get stuck at the critical. So I will discuss this question of how to choose P in this talk. So first, I will tell you about the literature. We'll see that in practice, it seems that when P is chosen of the order of the optimal rank, possibly slightly larger, but not much larger, Riemannian optimization algorithms work. This phenomenon is understood from a theoretical point of view, but only in very particular situations. And in a general setting, we understand, so the literature tells us how it works and that it works when P is larger than square root of 2m. But these theoretical guarantees do not match the empirical observations that its algorithms tend to work when P is of the order of the optimal rank. So we'll see that there is a gap between theory and practice, and we'll ask the question, why is this gap? And in the second part of the talk, we'll see that this gap is fundamental. It's not an artifact of proof techniques. It's possible to slightly improve the general result, which I will have discussed in the first part. But with this slight improvement, the result is optimal. So we see that in theory, if the factorization rank P is smaller than square root of 2m, even if the optimal rank R opt is very small, it's not possible to guarantee that Riemannian optimization algorithms work, unless we have some assumptions in the first matrix. And I give an idea of the proof of this result. And I will conclude, if I have time, with open questions. Okay, so let's go with the literature. So the Burer-Montero heuristic has been introduced by precisely Burer and Montero in an article in 2003. In this article, the authors performed various numerical experiments on problems in particular arising from max cut problems and minimum bisection problems. So in their experiments, they used the factorization rank equal to square root of 2m. And they observed that with this choice of factorization rank, there was no issue with critical points. Riemannian algorithms always work. They found the global minimizer of the factorized problem without getting stuck at a critical point. they did not try smaller values of p. In an article by Journet, Bach, Absil, and Sepulcre, years later, there were numerical experiments on max-cut relaxations. So the authors, they used a specific algorithm with a particular initialization scheme. But with this precise algorithm, they observed that as long as so even when the factorization rank was exactly equal to the optimal rank, the Riemannian algorithm they used worked. It always found a global minima. Then I would also like to mention an article by Nicolas Boumal in 2015 on another set of semi-definite programs. So on these semi-definite programs, the optimal rank was known to be 3. And Nicolas Boumal observed that his algorithm found the global minimizer of the problem as soon as the factorization rank was at least 5. So slightly larger than R opt, but not much larger. And similar results have been reported on problems which are not exactly semi-definite programs, but which look like semi-definite programs. So these empirical observations tend to corroborate the fact that as soon as the factorization rank P is slightly larger than R opt, there is no issue with critical points, and Riemannian optimization algorithms work fine, although they are applied to a non-convex problem. In specific situations, this has been explained. Rigorously explained. This is in particular the case in an article by Bandeira, Boumal, and Voroninski. In this article, the authors considered semi-definite programs arising from problems which are called Z2 synchronization and community detection problems. They made very strong assumptions on the underlying synchronization and community detection problems. They had a very specific setting, but in this setting, they could show that, so with high probability, the semi-definite program they considered had a solution with optimal rank equal to 1, and that if the factorization rank P was equal to 2, it was possible for Riemannian algorithms to find the global minimizer without getting stuck at critical. And similar results have been obtained for other problems, which are essentially variants of semi-definite programs. And in all these results, the principle is the same. The authors, they must assume strong assumptions on the problems which they consider. And under this strong assumption, they can show that provided that the factorization rank P is larger than the optimal rank, even if it's equal to the optimal rank, they find so Riemannian optimization algorithms work. They find a global minimizer without getting stuck. So we see that in a few situations, we have rigorous explanations on why the Burer-Montero heuristic works even with the factorization rank P very close to the optimal rank. But of course, these are only very specific situations, so we'd like to have some general guarantees. And the general guarantees, so actually there is only one result about general guarantees which I'm aware of. It's again due to Boumal, Voroninski, and Bandeira. And I'm going to describe it now. It's the starting point of our work with algorithms. So in this work, Boumal, Voroninski, and Bandeira, they assume only one thing. They assume, it's an assumption that I've already made at the beginning, they assume that the set of matrices B which satisfy the constraint A of B transpose equals B is a manifold. So Their assumption is slightly more technical, but in most applications, it will reduce to the fact that this set is a manifold. Under this assumption, they say that it's known that Riemannian optimization algorithms, at least suitable Riemannian optimization algorithms, not all of them, they typically converge to second-order critical. What I define as a second-order critical point is a matrix V0, which satisfies the constraint. I forgot to say it, but the set of matrices satisfying the constraints, I will denote it by MP. So a second-order critical point, it's a matrix V0, which satisfies the constraint, so it's in MP. At which the gradient of the cost function, the Riemannian gradient, is 0, and the Hessian of the cost function is semi-definite positive. So Riemannian optimization algorithms, they typically converge to a second-order critical point. And Boumal, Voroninski, and Bandeira, they can show that for almost all cost matrices C, provided that the factorization rank P is larger than this rather complicated quantity, so something which looks like square root of 2m, all second-order critical points are global minimizers. As a consequence, if Riemannian optimization algorithms find a second-order critical point, they find a global minimizer. So this means that provided that P is larger than essentially square root of m, Riemannian optimization algorithms work. You observe that in this result, the lower bound on the factorization rank, it depends only on m. It does not depend on the optimal range. So whether the factorization rank is 1 or of the order of square root of n, this does not change the lower bound. So to summarize, we've seen that in numerical results show that Riemannian optimization methods, they seem to be able to find a global minimizer as soon as the rank, the factorization rank P's of the order of the optimal rank are up. But the only general guarantee which we have says that algorithms work when P is larger than square root of 2m. And I've said that in many applications, R opt is of the order of 1, so there is potentially a big gap between these two numbers. So the question which we'd like to understand is it possible to obtain general guarantees, which are not problem specific, for ranks P smaller than square root of 2m? And we're going to answer this question by the negative. We'll see that it's possible to very slightly improve the general results by Boumal, Voroninski, and Bandeira, but it will not change the leading order. So we'll still need the factorization rank to be of the order of square root of 2m so that our result applies. And with this improvement, the result is essentially optimal. So even if the optimal rank is much smaller than square root of 2m, it's not possible to guarantee that Riemannian optimization algorithms work, whatever the cost matrix C, if the factorization rank P is not equal, at least equal to square root of 2m. So we start with the first part of this program. So the minor improvement over the general result. So we can show the exact same theorem as in Boumal, Voroninski, and Bandeira, only with a slightly different lower bound. We can show that provided that the factorization rank P is larger than square root of 2m plus 9/4 minus 3/2, then all second-order critical points of the factorized problem are global minimizers. Hence, Riemannian optimization algorithms work. So you can check that this is indeed an improvement over the result by Boumal, Voroninski, and Bandeira, in the sense that the lower bound that we have is smaller than theirs. However, the difference between the two lower bounds is very small. It's 1 in almost values of n. So unless n is very small, it doesn't make a big deal. So this improvement seems disappointing, but it's optimal. It's not possible to do better. So we have a theorem which describes that. So it's as follows. We need to define R naught as the smallest range of a matrix which satisfies the constraints. So the smallest range of a matrix X which is semi-definite positive and for which A of X is equal to B. And with this definition of R naught, we can show that under some technical assumptions, which I'm not going to describe here, if the factorization rank P is smaller than this quantity, which is slightly complicated, but where the most important term is the first one, square root of 2m, you can show that there is a set of matrices C with non-zero Lebesgue measure, for which the semi-definite program has an optimal solution, a global minimizer with rank R naught. And nevertheless, there is a second order critical point, which is not a global minimizer, which means that if we run a Riemannian optimization method and we are unlucky with the way it's been initialized, then it's possible to get stuck at this bad second order critical point, which is not a global minimax. So when P is smaller than essentially square root of 2m, it's not possible to guarantee that the Burer-Montero heuristic works, in the sense that there are cross matrices C for which there exists bad second order critical. So two comments. The first one is that R naught is typically small for most applications of interest. Typically, even R naught can be equal to 1. So it's much smaller than M. And the second comment is that our results lead to the following picture. If the factorization rank P is larger than square root of 2m plus 9/4 minus 3/2, then we can guarantee that Riemannian optimization algorithms work. On the other hand, if the factorization rank P is smaller than square root of 2m plus this thing that depends on R naught, we cannot guarantee that Riemannian optimization algorithms work. In between the two bounds, we don't know what happens, but the difference between the two bounds is very small. We can check that it's smaller than R naught minus 1, so it's of the order of 1. And when R naught is equal to 1, it's even 0. So this paints a rather complete picture of when Riemannian optimization algorithms can be certified correct, whatever the cross matrix. Let's briefly go over an example. Let's consider semi-definite programs which arise as max-cut relaxation. So max-cut relaxations are precisely relaxations, so an approximation of maximum cut problems, which are important and widely studied problems from graph theory. And their relaxations are semi-definite programs of the form represented at the bottom of the slide. So minimize the trace of Cx under the constraint that the diagonal of X consists of only coefficients equal to 1, and X is semi-definite positive. semi-definite programs with this form are important besides max-cut relaxations because they appear in as convex relaxations of other types of inverse problems, including phase retrieval or liquid synchronization problems, which I've mentioned before. So if we consider a semi-definite program with the max-cut form, so where the linear constraints are only these diagonal constraints, and if we apply the Burer-Montero factorization to it, what we have is minimize the trace of CVB transpose over all matrices V, such that the diagonal of VP transpose is equal to 1. It's an especially nice factorized problem because the constraint that the diagonal of VP transpose is equal to 1 is equivalent to the fact that the lines of V each have norm 1. So the feasible set forms a very nice manifold. It's easy to optimize over this manifold. And so in this case, we can check that R0 is equal to 1. We can also check that the technical assumptions which I've not described are satisfied. And therefore, we can apply our theorems. And they say the following. When the factorization rank P is strictly larger than square root of 2n plus 9/4 minus 3/2, then for almost all cost matrices C, there are no spurious second order critical points. Hence, Riemannian optimization algorithms always work. They find a global minimizer of the programs which they are applied to. On the other hand, when the factorization rank P is smaller than square root of 2n plus 9/4 minus 3/2, then even if we assume that there is a rank 1 solution, it's possible for some bad cost matrices C, there are second order critical points, hence Riemannian algorithms can fail. It's not possible to certify that they are correct without assumptions on C or on the initialization strategy. So I would like to try to give you an idea of the proof. So let's fix factorization rank P smaller than our complicated quantity, so the lower bound that we have in the theorem. And what we want to show is that there is a set of cost matrices C with non-zero Lebesgue measure, for which the semi-definite program has a solution with rank R0. And nevertheless, there is a second order critical point of the factorized version, which is not a global minimizer. The proof is in 2 steps. The first step is to construct one cost matrix, C. And the second one is to show that in a small ball around this matrix, the same properties still hold. Which means that if we can construct one C which satisfies the 2 properties of the previous type, then we can construct a whole set of such cost matrices C with non-zero Lebesgue measure. The second step uses only very classical geometrical arguments, so I will not discuss it. I will focus on the first step. So we want to construct one bad cost matrix for which there is a second order critical point, which is not a global minimizer. So for the construction, we fix a feasible matrix X0, a matrix which satisfies the constraint and which has rank R0. And we also fix a feasible matrix B, so in the feasible set of the factorized problem. And now the idea is that we are going to construct C such that the semi-definite program associated to C has X0 as a global minimizer, a unique global minimizer. But the factorized problem has a second order critical point at V, And this second order critical point is not optimal. So it turns out that almost whatever the choice of x0 and b which we've made, it's possible to construct a cost matrix C which satisfies these two properties. So how do we do it? So I've written the two properties again, which we want. So we want x0 to be, so we want a cost matrix C for which x0 is the unique global minimizer of the semi-definite program, and B is the second order critical point of the factorized call. Using the fact that the semi-definite programs, as well as its factorized version, they have gradient and Hessians with explicit forms, we can rewrite these two properties into analytical forms. We can try to simplify these forms, and after a few computations, we arrive at the conclusion that it's possible to construct C for which these two properties hold, provided that there exists mu, a vector mu in Rm, for which the matrix B transpose A star mu V is semi-definite positive, and x0 transpose A star mu V is 0. So I don't have a good geometric interpretation for these quantities, but these are the conditions which arise from the computations. They are simple, and so what we have to wonder is only when is it possible to work? So for which choices of x0 and b is it possible to guarantee the existence of such a mu? So when does there exist mu such that BP transpose A star mu V is semi-definite positive and x0 transpose A star mu V is 0? So to find out, we define the map which to mu associates B transpose A star mu V, x0 transpose A star mu V. So it's a map from Rm to the set of symmetric P by P matrices times R, so the set of matrices with R not rows and P columns. We can compute dimension of the range, so of the image. It's P plus 1 over 2 plus P R0, while the initial space has dimension M. So we can say that when the dimension M is larger than P plus 1 over 2 plus P R0, a priori, the map should be surjective, because a relatively generic map between two vector spaces such that the dimension of the first vector space is larger than the dimension of the second one, it's usually surjective. And if the map is surjective, then mu exists, because we only have to choose for mu, for instance, the elements for which the map, whose image by the map is the identity and 0, the product identity 0. So as soon as this map is surjective, then there exists mu as we want. And with the technical assumptions that I've hidden into the carpet before, we can say that, yes, the map is surjective, provided that the inequality holds, the inequality between the dimensions. And if we rewrite this inequality under a different form, we arrive at the inequality on P, which is exactly the one that we have in the theorem. So this ends the proof sketch. I wanted to show it to you so that you have an idea of why the lower bound, the upper bound, sorry, on P appears and why it has this rather complicated form. So it's this kind of dimension counting argument. So let's now summarize. We've seen that when the factorization rank P is larger than square root of 2n, then the result of by Boumal, Voroninski and Bandeira said that for almost any cost matrix C, Riemannian optimization algorithms work. However, numerical experiments suggest that it might be true for factorization ranks much smaller than square root of 2n. And what we've shown is that, no, actually it's not true. Despite numerical evidence, it's possible that Riemannian optimization algorithms fail when the factorization rank is smaller than square root of 2n. They do not always fail, but they can fail, so that it's not possible to guarantee with certainty that they work. There are cost matrices C for which they may. And I would like to briefly discuss two open questions. So the first one is more theoretical and the second one is more applied. So the first one is about understanding in a more detailed manner what happens when P is smaller than square root of 2n. So indeed, to summarize the guarantees, the theoretical guarantees which I described in the literature review, we can say that there are two types of theoretical guarantees. So in very specific situations, so with very strong assumptions on the cost matrix C, we can show that Riemannian optimization algorithms work when P is the optimal rank R of, so possibly the optimal rank plus 1. So if the cost matrix C is very nice, then Riemannian algorithms work for P of the order of the optimal rank. Our results, so the general result by Boumal, Voroninski and Bandeira, on the other hand, says that with no assumption on C, it works for P larger than square root of 2n. And we've shown that this is optimal, so we could summarize this by the sentence: when the cost matrix C is allowed to be arbitrarily bad, arbitrarily pathological, then it's necessary to have P at least equal to square root of 2n. But in most applications, the cost matrices C which we encounter are not as nice as what has been assumed in some work on the subject, but they are not totally pathological either. There is some in between. So it would be interesting to have a result which would also be in between, something like under some assumptions on C, but not stringent ones, Riemannian optimization algorithms applied to the Burer-Montero factorization work for P of the order of the optimal rank, but possibly like twice the optimal rank, something like this. This is the first open question. The second one is how does the Burer-Montero factorization applies to a specific family of semi-definite programs arising as convex relaxations of phase retrieval problems. So just one slide on what phase retrieval problems are. Phase retrieval problems are inverse problems of the following form. So we want to reconstruct X, some unknown vector with complex coordinates, from the modulus of linear measurements over X. So the modulus is the standard complex modulus. The linear measurements are obtained by Hermitian product between X the unknown and known measurement vectors A1, A2 to AM. This family of problems has important applications in optics. It has therefore been studied since the 50s, so quite a while. There are several algorithms known to solve phase retrieval problems, but one important family is based on convex relaxations and so on semi-definite programs. And it's known that, so at least numerically, what it seems is that these algorithms, they have a good reconstruction quality, but they are extremely slow because of the fact that there is a semi-definite program involved. And so the question which I'd like to understand is it possible to apply the Burer-Montero heuristic to semi-definite programs arising as relaxations of phase retrieval problems? And especially, so that it works well, how must we choose the factorization rank? I've done preliminary numerical experiments, and they seem to suggest that it's possible to a small factorization rank works fine, but the good choice for the factorization rank seems to depend on the precise phase retrieval problem which we consider. So it must be probably adaptively chosen. And I think there is possibly some theoretical understanding which can be gained about this and which would help for designing an efficient algorithm. This is the end of my presentation. Thank you very much for listening. And of course, if you have questions, they are welcome.